Divergence test and integral test. Video 2. On DT, the last video, we saw that if the sequence defining a series does not go to 0, or if the sequence doesn't have a limit, then the series that it defines will diverge. Here in video 2, we're going to look at the integral test. So integral test. Well, we know that if we want to do an integral, we're going to involve a function, but we're studying series, so we have to bring those two together. Let's start first with our assumption on the series. We're going to assume that the series has a sequence of positive terms. For the function, we want 3 different conditions met. We want to be able to integrate, so assume that it's continuous. We want the function to decrease, so the graph will look like that. And at every integer value after some starting integer, that the function and the sequence agree. So 3 conditions on the function, 1 condition on the series that the terms are positive. Good. Let's get going. There will be 2 different parts to the statement. On the first part, let's take a look at the picture. Remember that the function is continuous, so the graph is nice. It's decreasing, so it continues to go down. And that the sequence and the function agree at integer values. So because they agree, we can take the height of this rectangle and multiply it by 1 to get an area, and then that area will exactly equal A1. Very nice. Taking a look, we can see that the rectangles leave a gap underneath the graph of the function. Let's write that down. If we start from 1, look at the function, integrate out to some value, we can associate that integral with the area under the curve, this quantity here. Notice that if we take our heights and pull to the left to get a box, that starting our integral at 1 would leave off the very first box. So adding it in, we're then able to say that this quantity is larger than the sum of the boxes, and we can identify the sum of the boxes as the kth partial sum. Excellent. Let's make draw some conclusions from this. All right. So here's what we were just looking at. And we're adding in this idea that A1 is A1, but that integrating from 1 to k is going to be smaller than integrating from 1 to infinity. Nice. No worries there. Make an assumption. Let's suppose that the integral from 1 to infinity of the function is finite. Well, then each of these guys, s sub k, will be less than this finite quantity. What does that mean for the sequence of partial sums? That means that the sequence is bounded. Good. So we're making an assumption and getting a result. Take a look at the kth partial sum. It's adding terms from the sequence of positive numbers. Because the sequence has positive numbers, that tells us that the sequence of partial sums is increasing. You can write that down. sk is adding up the first k terms of the sequence. sk plus 1 is adding in a sub k plus 1, so it's going to be bigger, and so forth. This is an increasing sequence. Nice. If the sequence is both bounded and monotone, then the sequence will converge. Fantastic. That's part 1 of the integral test. Good. Now what we're going to do is we're going to push the boxes to the other side. What do we mean by that? Here we go. So we're using the same a1, a2, a3, and so forth by looking at an integer, evaluating the function. Instead of pulling the box to the left, we're going to pull the box to the right. Since f is a decreasing function, this will result in the boxes giving an overestimate of the area under the curve. Notice that if we look up at n and then pull to the right, that box will finish at n plus 1. So if we look at n up to the right, that the base of the box will sit between n and n plus 1. So if we're going to start at 1 and then go out until, for example, a sub 4, that we should consider the portion under the curve from 1 to, not 4, but 1 to 5. In other words, you want to focus that here we have bounds from 1 to k plus 1 to give a lower estimate to the kth partial sum. Good. We're doing the second part here, and we're seeing that we get overestimates by the kth partial sum of the integral. Okay, so what is this going to give us? Well, if we now make the assumption, instead of converging, that the integral, the improper integral, diverges, then that's going to tell us that the sequence of partial sums is unbounded. So if this is tending out towards infinity, and the corresponding partial sum is always bigger, then this guy must get as large as we like. Because sk is a monotone increasing sequence and it's unbounded, we're finding that the sequence of partial sums also diverges. That's part 2. Let's bring this all together. Statement of both part 1 and part 2. So if we have underestimates, and we're able to show by computation that the improper integral is convergent, then so will the series be convergent. On the other hand, if we have an integral which is divergent, because that is infinite area, then the overestimate of the partial sums will also diverge. So the statement is that if we have a function which is continuous, decreasing, and at integer values after some index, always equal the positive terms of a sequence, then both the series and the improper integral either diverge or both converge. They go hand in hand. And that is the integral test. Excellent.